We're going to talk binomial theorem from Algebra 2, and then we're going to work it into calculus. The binomial theorem is a major shortcut for having to keep foiling things out. If you FOIL out x plus y squared, you probably already know that it's x squared plus 2xy plus y squared. What you may or may not pay attention to, however, is that there are ones on the coefficients of the first and last term, and 1, 2, 1 happens to be a line in Pascal's triangle. In fact, here's line 1. It's line 2 of Pascal's triangle. And line 3, 1, 3, 3, 1. Again, remember Pascal's triangle, if you add the two numbers next to each other and go diagonally down, that gives you the next number. So the fourth line would be 1, 4, 6, 4, and then of course a 1 at the end. So if you want to cube a binomial from Algebra 2, x plus y to the third, you don't have to fumble around by foiling it 3 times. All you simply do is take line 3 from Pascal's triangle, this 1, 3, 3, 1, use that as your coefficients, and then simply start with this power of x, so x to the third. The x's will lose power, so x to the second, x to the first, no x's at all in the last term. And the y's will grow. Notice there's no y's in the first term. Y to the first, y to the second, and finally 1 y to the third. One thing to notice in the binomial theorem, if I go ahead and put these exponents on, is the exponents will always add up to this. So this was third power. This we have a 3 and 0. We have a 2 and a 1, 1 and a 2, and finally 0 and 3. So that way you won't lose track of where you're at. If you want to do x plus y to the fifth, again, the binomial theorem is so much faster. The fifth line of Pascal's triangle, the line right below this one, will be 1, 5, see, 4 plus 6 is 10, another 10, 5, and finally 1. These lines of Pascal's triangle are always symmetric. We call them palindromes, just like words like, Bob or race car, where they're the same forwards as backwards. So it's 1x to the fifth. And again, the x's lose power, so x to the fourth, third, squared, x to the first, no x's at all. The y's start to gain strength. Squared, third, y to the fourth, y to the fifth. I'll turn that into a plus sign. Let's put some plus signs in the middle. And there you go. That's x plus y to the fifth, much faster than doing it the long way and actually foiling it out 5 times. Oh my gosh, that'd be crazy. Why do we use this? Well, we're going to step it up a notch right now. Sometimes they'll simply ask you for the first 3 terms. A lot of times this is a good AMC or OML question. Certainly you're not going to go down to the 13th line of Pascal's triangle and try to start figuring it out. You just simply want the first 3 terms. Well, the first term in any line, the first coefficient is a 1. Since this happens to be line 13, I know that the 13 is going to come next. But the third coefficient in is a little more dicey. It's kind of tougher to tell. Let me start off with the x. It'll be 1x to the 13th plus 13x to the 12th, y to the first, plus some other number I'm not sure about, x to the 11th, y to the second. Notice the x's are going down each time the y's are coming up. But again, I don't want to make 13 lines of Pascal's triangle to figure this out. There's an easy way to do it called the binomial theorem. And what the binomial theorem says is you'll start every line of Pascal's triangle with a 1. Okay, that's just kind of obvious. The second term in is the line number, so it's 13. I'm going to write down that 13. But I'm going to put a 1 below it, just because I can. The next term, believe it or not, you take the numerator and you go down by 1, so multiply by 12. You take the numerator and you come up by 1. multiply by 2. Of course, the 12 and the 2 are going to cancel each other. 13 times 6 is 78, and that is indeed the coefficient. So here are your first 3 terms using the binomial series. Just to illustrate the power of the binomial series, I can recreate row 4. Obviously, here's Pascal's triangle, so we know that this row is legit. The first term, of course, is a 1. It always is. The second term in is the row number, so it's a 4. Again, if you want to see the next term, multiply the top by 3, the bottom by 2. Again, that's going to cancel the 4 and the 2, and you can see there's the 2 times 3, there's the 6. If you want the next term, keep the pattern going. Go down, so that would be times 2, and come up. Well, obviously, those 3's are going to cancel out. You have 2 times 2, which, of course, is the 4. And finally, all the lines end with 1, because by the time you get back to where you started, if you keep coming down by a power and multiplying by 1, and going up by a power and multiplying by 1, you can see that you have 4 times 3 times 2 times 1 in the numerator and denominator, and that makes sense. So the binomial theorem can be used to quickly grab any row of Pascal's triangle without having to write the triangle out and solve it. This is also extremely useful in probability. We always have done problems with fair coins, 50-50, heads, tails. But what if we have a coin that's rigged and it comes up heads 80% of the time? Or what if we have 2 athletic teams playing each other and one team is very much better than the other team? Maybe they would win 80% of the games against this opponent, and they're playing a 3-game series. We can use the binomial series to help us figure out probabilities of certain things happening. All right, so let's say that this coin is rigged to go 80% heads. We're going to flip it 3 times and see what happens. This is simply a binomial distribution. What I mean by that is there's only 2 things that can happen. It's either going to land heads or it's going to land tails. Sure, you'll hear people say, "Oh, what if it lands on its edge?" I just laugh at them. So no, we're not going to go there. So it's either going to be heads or tails. So we do heads plus tails, and we take it to the 3rd power because we're going to flip it 3 times. If we flip it 4 times, we take it to the 4th, and so on. Okay, if you do the binomial expansion of this, basically the h is your x, the t is your y, and you would have 1 h to the 3rd. Again, I'm going to use the 3rd line of Pascal's triangle, which is 1, 3, 3, 1. So we have 3 h2 t1, so 2 heads, 1 tail. Another 3. This time we have 1 head, 2 tails. That's the tails squared. And finally, 1 tails to the 3rd, if you will. Okay, that's the binomial series. Expand it out. But now we can put the probabilities in. It says that the heads come up 80% of the time. So that's 0.8 for heads. And that would make sense that the tails should be the rest of it. So the chance of this coin coming up tails would be 20%. Let's go ahead and fill in what we know. So heads is 0.8. So this is going to be 0.8 to the 3rd power. Plus 3. And again, we're going to have 0.8 for heads. That'll be squared. And then we have the tails this time, and the tails is 0.2. And I just went ahead and finished out the distribution. Now we can mathematically figure out what this is. 0.8 times 0.8 times 0.8 is 0.512. So if you flip this coin right here 3 times, you'd have a 51.2% chance of having it come up all 3 heads. Heads, heads, heads. If you go 3 times 0.8 squared times 0.2, that's going to be 0.384. So there's a 38.4% chance of it becoming heads twice, tails once, in any order. And not surprisingly, the probability decreases. This is 0.096. There's only like a 9.6% chance of getting 2 tails on a rigged coin. And for a rigged coin to come up tails, tails, tails all 3 times is 0.008 or less than 1% of the time. By the way, if you add these probabilities together, it will add up to 1, and it has to add up to 1 because that would represent 100% of the time of trials occurring. So it makes sense. So there is your distribution. And again, we used the binomial theorem and made a little binomial series up, and then just put in the probabilities. This is the binomial series that I just taught you, but it's written in a little bit more of a formal way. I think it'd be a little easier for me to teach it if I, instead of using k, just kind of turned it into a number. If I was in class live, I would just ask you guys, hey, what do you want k to be? But since nobody else is around, I'm just going to pick a number. Let's have k be 5. That sounds pretty exciting. 1 plus x to the 5th would look like this. You would have 1 to the 5th, and you'd have 1 to the 4th, and the 1s would lose power each time. Not that 1s are very powerful anyway, but you kind of get the idea. Until eventually we ran out of things. The x's, on the other hand, would start to gain power. Now, there are no x's in the first term, but then the x's will start to increase. X to the first, x to the second, x to the third, and so on. Since we're in the 5th row of Pascal's triangle, that's 1, 5, 10, didn't leave much room for myself, 10, 5, 1, and so forth. You kind of get the idea. But look what's happening here. This 1 is right here. This kx makes sense, because remember, k is 5, so this should come out to 5x, and it does. This next one is 10x squared, and that makes sense because here's your x squared. How do I know it's a 10? Well, easy. Remember, k is 5, so we have 5 times 4 over 2 factorial, but remember, 2 factorial is 1 times 2. You can see that I'm doing the binomial theorem. This is 1 times 2 times 3. The denominator is growing by 1 each time. The numerator is shrinking. Again, k is 5, so this is 5 times 4 times 3. Again, the 3's cancel. This is 20 over 2, which is this other 10. And so it makes sense that the complex binomial series formula that's on your laminated sheet is really just the same thing that we were doing up here when we were doing our coins. It's really just Pascal's triangle. All right, finally, we're going to link the binomial series to some calculus. It says use the binomial series to find a Maclaurin series for the function. All right, we know this is going to be Maclaurin. It doesn't look Maclaurin at first. It almost looks like it's going to be centered around x equals -1, but it will not be. It's going to turn out to be Maclaurin. And the reason why is we know that 1 plus x to the 4th, if we go term by term, it will start with a 1. It'd be 4x. And again, notice I'm using the binomial theorem. You may not really realize it at first, but this 4 is really 4 over 1. And then this is, of course, 1 times 2. The next one's going to be 1 times 2 times 3. So you're going to see a 3 factorial. Again, once you cancel some things away, you'll get your final answer right here. And you can see that everything works out. There's the 1. That's your 4x. Again, 4 times 3 is 12, divided by 2 is 6x squared. Here, your 3 factorial is 3 times 2 times 1. That'll cancel with this 3 times 2, leaving you with a 4. And 4 times 3 times 2 times 1 is 4 factorial. Again, notice that you've got line 4 of Pascal's triangle. 1, 4, 6, 4, 1. The 1s start out almighty. This is 1 times 1 to the 4th, even though it doesn't show up, and the 1s get smaller. The x's start out non-existent here in the first term, and then the x's grow. First power, second, third, until all 4 are x's. So the binomial series does give you Maclaurin series, This Maclaurin series in the green box, as you can see, is centered at 0 because there's no parentheses required. So really, the binomial series is more or less just straight out of Algebra 2. What can make the binomial series a little tougher is when you have a negative power. So what's 1 plus x to the negative third? Well, again, the binomial series still works, but man, it's just complex. And more disturbing, it's never ending. Because normally, you would go until you reach 1. That will never happen here. The numerator is just going to keep gaining terms, and you'll never end. So for this, you just have to express it with a little dot, dot, dot at the end. We can end up turning that into a summand, though, and that's going to be a little trickier, and hopefully I can help you understand what I'm doing here. I simplified each term and brought everything down. I even simplified a few terms that we can't see just to give you an idea of the pattern. Now, some people will recognize what's happening here. Other people will not. But even the people that recognize the pattern have a hard time making a formula out of it so that a machine like a computer can recognize it. These numbers, a lot of times, are called triangular numbers. 1, 3, 6, 10. Imagine a pyramid, maybe a bunch of cheerleaders, maybe there's 6 of them, and they can make a pyramid. 1 person on top, and then 2, and then 3. That's 6. If you want to add a bottom row, 7, 8, 9, 10. It's like a big stack of bowling pins. If you want to really get daring and add a bottom row, 11, 12, 13, 14, 15. So you can see that the numbers are all pyramidal numbers, if you will. You're adding 1 more than the number before. But then you've got this alternating component thing going on at the same time, and that can be challenging to write a formula for. So we're going to talk some pattern recognition. Believe it or not, a few years back, I was the commissioner for a church softball league, the Nordonia Men's Church Softball League. And I had all the wonderful duties of finding umpires, getting the fields from the cities. You know, obviously they'd charge us for the fields and you had to pay the umpire fees. And I had to do a little bit of book work. And so one of the things I had to make sure of was that we had enough money and we had enough umpires. So our league at the time was 11 teams. Obviously, if you only have a 2-team league, it's kind of boring. You just play 1 game and everybody's played each other. With 3 teams, it's 3 games. If you have teams A, B, and C, real easy. A plays B, A plays C, B plays C. Everybody takes a game off. It gets a little more complex when you start adding more teams. With 4 teams, well, it's going to be 6 games. With 5 teams, it takes 10 games for everybody to play everybody else. And that was our league format. You can see the same pyramidal numbers are in this problem as well. So when we had 11 teams, I had to figure out how many fields to get. We played doubleheaders, so I had to figure out, this is the field dates, then there's rainouts and everything else that went on. But with 11 teams, it was really easy. It was 55 games. Now that might appear like 11 times 5, but that's not why it's 55. Here's really what's going on. If you have 5 teams, let's say we're one of the 5 teams, Beechwood. How many teams do we play, or how many games do we play? We play 4 because we don't play against ourselves. That's called a scrimmage. So 5 times 4 would be 20. But we have to divide by 2 because we don't want to double count the games. Beechwood versus Orange is the same game as Orange against Beechwood. So this dividing by 2 just eliminates the double counting. That gives us 5 times 2, which is 10. So same thing with 11 teams. You have 11 teams. Each team's going to have 10 games. But we divide by 2 to eliminate the double counting. It is, in fact, 11 times 5. That's just coincidental. So 55 games. So if you have a random number of teams and you want to play a round-robin tournament, the formula is simply number of teams times n minus 1. And again, we divide by 2 to eliminate that double counting. That way, Ohio State versus Michigan does not count as a different game than Michigan versus Ohio State. It's the same game. All right, let's take this back to our calc example. So again, it's n times quantity n minus 1 over 2. That'll be the way that we generate the pyramidal numbers. All right, so here's our final answer. Now, the thing about it is this summand does not look like the thing I just said. Obviously, the -1 to the n is going to cause the alternating component. But I had n times n minus 1 over 2. I can see the 2, but I don't have the correct things here. These are off. These don't match. In fact, they're off by 2. But that makes sense because remember my example, the smallest number of teams I could have would be 2 teams. That's not much of a very fun league. You just play each other. This starts at 0, so it makes sense that I'd have to, adjust the summand by 2. And so since I'm taking away 2 here, I have to add 2 to the insides to make it balance. It is the same formula that you use in the round-robin sports tournament or many other applications to figure out the binomial theorem. So hopefully that analogy helped you guys out a little bit.